Hello everyone and welcome back to another Max MSP Neural Networks tutorial. Last time we built this patch here, which is designed to be a single neuron which can take a list of data, work out a pattern from it, and then be able to give a pretty good guess from new information as to what the answer should be. Now you can see there's a couple of little changes here. First of all, I got a load of really good feedback on the Facebook Max MSP group, which if you're not a part of, go and join it, it's wonderful. A lot of people were talking about better ways to work through all of the data than counter objects. So we've got a couple of Uzi objects here instead. So it'll go through 1, 2, 3, 4. If you don't know, with Uzi, out to the leftmost inlet, it will do a number of bangs. Outlets, sorry, not inlet. It will do a number of bangs depending on what your argument is. But out of the right inlet, it will do an index of that bang. So it will do like 1, 2, 3, 4 in this case. So we've done a -1 into our get row, so that gets that, and then that will do it 10,000 times. And that does it practically instantaneously. It's really good. The only other change that I've made to this patch since the last video is this bit here. The way I did it before, I just did it the other way around. I forgot that you could do the exclamation mark minus object, so just look at that, compare it to the previous way. This is slightly simpler, it doesn't make much difference. One other thing that some people gave to me in feedback was that when you go through this, and in fact let's just go through it again. If we randomize the weights and then do this, and then here we go. So now if we do one of the new bits of information, we click on this, the answer should be 1. So yeah, it's very close to 1, and this should be 0, very close to 0, lovely. But as some people pointed out, when you try a few different values, such as 0, 1, 0, which in this case the answer should be 1, because if you remember we're going from the first inlet, the first input being the correct one, we get an answer of 0.44. Now obviously that's still closer to 0 than 1, so yeah, the answer should be 0. But it's not that close. And initially I wasn't quite sure why, but if you have a look at the weights, it's pretty obvious, because the first weight has a very strong positive weighting, obviously, and the third weight has a strong negative weighting, but the middle weight doesn't really have much of a negative weighting at all. And the reason for this, I worked this out, and it was not actually a problem with the patch. In fact, if we go back to the original article we took this from and have a look at his results at the bottom, we see that he ended up with pretty much the exact same weights. And had he put in 0, 1, 0 instead of 1, 0, 0, he would probably have got pretty much the same result. And I think what it is the training data itself is less than optimal for getting the perfect weightings. And the reason for this is when each of the inputs is 1, that is the only time when the weight is actually adjusted. Because if you remember, we multiply down here, we multiply by the input. So when the input is 0, the adjustment also becomes 0, because whatever else we've done, we've multiplied it by 0, so it's nothing. And here, the second inlet, it's only 1 twice. And one of those times, the output is also 1. So it's like half the time the patch, or the neuron, is thinking, well, actually, this is right, this is the same. And the other half of the time it's saying, no, this is wrong. And it's obviously slightly more confident that it's wrong than it's right, because otherwise we wouldn't have got a negative value at all. But it's obviously not enough for it to be certain enough about it. And I've actually come up with a slightly better set of training data that makes it more obvious and makes the patch more confident about it, but we'll get to that at the end of the video. Okay, so what we're going to do today is we're going to take all of this and basically rebuild it, but we're going to abstract it so that we can build an object of a neuron just by itself, with inlets and outlets and all that lovely stuff. So if we make a new patch, first thing we're going to do is, if we want a neuron that we can create that has any number of inputs that we want, that's a little bit tricky, because as it is here, we've specified here in like the spray argument 3 and all of that, how many inputs it's expecting. We've got this many little bits of processing and this many p-vars for our weights. So we need to find a way to get the patch to do that dynamically. And there are a couple of ways of doing this. There is the v expression object, which I believe is to do with applying mathematical expressions to lists of numbers, which I think could get the job done, but I prefer to use the polytilde object. And polytilde, if you're not familiar with it, it does what it says on the tin. It's primarily for making an instrument or a synth that you've made in Max, taking that and making it polyphonic, so it's got multiple voices. And in this case, if we've got a neuron with X number of inputs, you can treat each of those inputs like a voice. So what we're going to need to do is we're going to need to make a patch, an object, for the neuron to use as its poly. So what we're going to do first, if you open a new patch, we'll do some inlets. Now if you haven't used poly before, it's not the inlet object, it's just in object, it says here, for a patch loaded by polytilde or pft tilde, and you have to actually number them this time as opposed to just them being numbered automatically. So here is in 1, and if we make a comment on this so that we remember what it is, this will be the initial weight that comes in when we randomize the weights initially, and we'll send that down into a float object. There we go. And then our in2 is going to be the input, so the 0 or the 1 or whatever. So that's fine, put that there. And then obviously the weighting and the input are going to be multiplied together. So we do a times float object, send that into there, and that into the cold inlet, so that as soon as the weight is adjusted, it's prepared there for waiting for when the inlet comes in, so they will then be multiplied together. We'll create our first out here, out 1, connect that up, and this will be weighted input out. Okay, so that's all fairly straightforward, and then for the all the stuff that does the adjustment to the weighting of the neuron, we'll need a couple of bits for that, and obviously the way I did it over in the previous patch was piece by piece to walk everyone through how it does it step by step, nice and easy, but it's much easier if we just do it in one simple object, which is the expression object, as a lot of people also pointed out to me online, which is very helpful. So if we do another in 3, what we want is the neuron, oh no, we want to do that as a comment. We want to do the neuron output. So once the neuron has output its initial guess, it will then send that back in through here, and the in 4, which needs to be the training output, so the correct output, the correct answer that's coming in. Now if we do below here a trigger with 2 floats, so it will send this float to 2 different places in a specific order. This is probably a little obsolete because obviously Max does read right to left, but if you're in any doubt, it's always good just to use triggers, because then you know exactly what order everything's happening in. And then we want to do the exclamation mark minus float here, so the training output into there, so that will come in first, and it will do that minus the output, which if you remember gives us the error. And then our lovely expression object, which is used to evaluate a mathematical expression. So if you remember, we have to do the error multiplied by the input multiplied by the sigmoid curve gradient, which, if you remember for that, it is the input times 1 minus the input. That's it. So, oh, sorry, the output minus 1 times. I can't speak. The output times 1 minus the output. There we go, we worked it out. Okay, so we're going to do open bracket 1 minus $F1. So the $1 is obviously for the first input that's going to come into this, and with expression and with several other objects like it, you have to specify if it's expecting a float or an integer or a character, anything like that. So we're doing 1 minus $F1 multiplied by $F1, so the which is going to be the output again, multiplied by $F2, which will be the input, multiplied by $F3. So that's a really simple expression actually. So the input here we'll put into 2, the error into there, and the output into there. Now the reason we're doing this and not putting the input in first is the neuron output is going to be the last of these 3 values that enters the neuron, because it's going to send the input in, and then obviously it will send out the weighted input, add those all together, do a bit of stuff to them with the sigmoid function, send it all the way back in, and then this output will trigger the calculation, which is what we want. So then we'll do a plus float object, trigger that. Let's move this down a bit and this all up a bit, because then if we connect these we get a nice little, we don't want that in the cold, we want that in the hot. There we go. Then we can drag these to the right, we get a nice aesthetically pleasing little infinity symbol there. So that is basically our neuron. And because we still want to be able to see what the weight is, we'll do one final inlet in 5, and this will be called display weight. So it'll be so that we can send a bang into this neuron, or this part of the neuron, to display what its weight is. So if we create one more float box, send that into there, and if we're very clever with our placement of this, we can make the line match up very nicely on there. Great, and that will then bang out the value stored there to out2. Let's keep that there. There we go. Comment weight out. Lovely. Okay, so now we need to save this. So if you've not done sort of saving your own patches and then opening them up by using patcher or bpatcher or poly tilde objects before, you'll need to save this in your Max file path. Now if you go into options and file preferences, you'll see libraries that Max has already specified as to where your stuff can be saved. You can then also add new files, new paths. So I've got my Max patches folder, which is in my documents folder, and this will be stored in there. Just wherever you're saving your stuff, Max needs to know where to find it, so just specify that in there. So save as, got this in here, which is a subfolder of my Max patches folder. We'll call this sub underscore poly. No, we won't. We'll call it sub neuron. Now, the reason I've used an underscore is when you give the name of something in Max, Max doesn't like you doing spaces, so replace a space with an underscore. That's the easiest way to do it. So that is that, so that's lovely. So now we can go on to building the actual neuron itself. So if we close that down, make a new patch up, and then we'll do poly tilde sub neuron. Lovely. Then if we lock the patch, double click on that to check, yeah, and there it is. So that is now there. So what we first need to do is send in values for the weights. Now the way that you access all the different voices in a poly tilde object is you can either specify it with an argument, the argument after the name, but that obviously keeps it static. We want it to be dynamic. So what we're going to do is we're going to make a message, voices, $1, and then here's the clever bit, we're going to do load mess #1. And again, if you're not familiar with #1, that means that when we load this patch, this final neuron patch, as an object, we can give it an argument. And whatever that argument is, so after we type the name, we type a number or a character or whatever that argument is, #1 will take the value of that argument. And you can do it with #2, #3, #4, etc. for as many arguments as you like, essentially. So we will then specify how many voices we want when we first load the neuron object up, if that makes sense. So if we send that into the first inlet of poly, so that is awesome. So now we want to sort out the weights. So again, we want an Uzi object with, once more, #1 because it's for how many voices we're going to have, or as many weights for inputs. We do our previous formula, which is random 101 minus 50 divide 50. Connect that all up. But we do not want those obviously to all go to the same one. We want each of the voices to have a different value. So what we're now going to do is create another message saying target $1, because with poly tilde, if you do target and a number, it will target that specific voice, and then any message you send to it after that will be sent specifically to that voice and that voice only. So because the Uzi object obviously sends out an index before it sends out each of its bangs, we can send that into the target $1 message. So it will do target 1, send out a random number, target 2, send out a random number. So it will target each of the voices in turn, sending them out a new random number, so each of the weights receives a different initial weighting. So that's great, that works there. Start tidying up some of these. Oh yeah, I discovered something completely new, again from one of the commenters on Facebook. Obviously, you know, Command Y cleans up your patch cables, makes them look nice, but I had no idea that you can do Command Shift Y, and it will automatically put them so that they avoid objects. Now this one doesn't look quite as good as some of the others have done, but you get the idea. It's quite nice and tidy, and makes your life a lot easier, so that's great. Thank you very much for that. So we need to do a load bang, because whenever we load it in, we'll just get them to be randomized initially. That's great. And then our first inlet, so that we can re-initialize all of the weights if we want, is there. And with the inlet, if we go into the inspector, you can go to comment and write a little something there. So we'll put initialize weights, bang. So I always put in brackets what type of information that inlet is expecting, just like most Max objects have, just for my own peace of mind. So if I ever forget what I'm supposed to be putting in there, I've got it there in black and white. So that's nice and easy. Okay, so that is there, so that's the first bit, and then the next inlet will be expecting the data that's actually coming in from our matrix control object. So we'll put this data in list. And then what we want to do with this, obviously, we want to be able to specify the difference between training data that's going to have the correct output attached to the end of it, and then non-training data after the fact that is just going to be the input values. So what we want to do is do gate2, send this into there, do a load mess 1, because we automatically want it to be open with the first outlet, which is going to go into list funnel, not list funnel, which will then index each of the list elements, and then we can unpack those. You can see I'm doing this slightly differently to how we did it before, because this just makes the most sense to do it here, because we're having to target each of the voices again. So we're unpacking both of those values, so it'll have the index and then the value of the inputs, which in this case will either be 0 or 1. But we want those the other way around, because again we're going to be targeting each voice with the index number. So we're going to use a swap object, which takes a list of 2 items and reverses them so that the first item comes out of the right outlet first. So then we want to do +1 to that, because the index will start at 0 and we want to start targeting the voices from 1. So let's move some of this down so it'll be easier to access. Go, send that into there, and that into there, I believe. I'll double check. So the second input is, yep, that's going to be the input itself. Perfect. Let's just unify those. Yeah, prefer that down there. Target $1, we also need to connect that to the first inlet. Lovely. Okay, so then the next bit we need to do for this, create another inlet. And this is going to be an inlet that lets us control whether the training mode is on or off. In fact, we haven't finished this gate bit yet, have we? I'll get to that in a second. So we do +1 so that we can send a toggle, which will either be a 0 or a 1 in there. Send that into the gate. So then the gate will either be 1 or 2, this or that, because 0 will mean that the gate doesn't send out of either. So then if it is 2, it means training mode is on, so it was going to expect the last item on the list to be the training output, which in this case we want to get rid of, or we want to send to a different place. So we're going to use that ZL equals object again. 1, send the list out to there, and then if you remember, out of the left outlet will come the list minus the sliced bit off. That there. And then the rest of that we're going to send to a trigger with F and B. So the float, the output value, is going to go into this bit here with it. Let's double check again. There you go. No, we need training output is inlet 4. That's that. So it needs to go into the 4th inlet. But because we want every voice to have that same output, that same correct output value, this is why we've got the bang. We're going to send it to a message of target 0. Because if you tell polytilde target 0, it will target every voice at once with the next message or messages you send it before you send it another target message. Okay, so that is that. And then the We also want one more inlet here. Which eventually we will do list weights. Bang. Okay, we'll come to that in a second. So out of polytilde, what we're going to get out of the first outlet is going to be the weighted inputs, which we want to send those into a ZL group object. And again, we want to give that argument #1 because we want it to group them up and send them out in groups of however many inputs we're expecting. So that's how we want that, and again the #1 argument will give us that. Send them into a ZL sum object, which is again really useful for lists rather than having to mess around with those multiple addition objects so that we get the sum of all of the weighted inputs. We use just ZL sum and it takes a list and then adds the entire list together. So that's great. And now we need to send those into our sigmoid function, if you remember from last time. Now, again, I built it bit by bit, but instead we can just use one single expression object. And if you remember, it is 1 over, open brackets again, 1 plus e to the power of our the negative x, negative whatever's coming in. So the way we do that is we do pow, open bracket again, do our value of e to 6 decimal places, which is 2.718282, and then you do comma, which specifies what you're raising it to the power of. We're going to do $F1, so the first thing that's coming in here, so the first input, times, open brackets again, -1. Because if you just put -1, it would get confused about the syntax. And then how many brackets do we have to close? 1, 2, 3, 4, 5. Lovely. So that's our sigmoid function right there. We can send that into there, and then we can send that to our first outlet, which we can call neuron output, and that will be a float. Great. So then we also need to send that, if you remember, back into polytilde to trigger the adjustment of the weightings. But again, we don't want that to happen every single time, because once we've finished training, we don't want the weightings to be adjusted, especially since we're not going to be sending new correct output values in, so it might take old output values that it's already got stored and change the weights, and that would completely mess it up. So again, we want to gate it, so just do regular gate, which just gives us one output, which is all we need, one outlet rather. Send that into there, and from the same inlet up here that specifies training mode for here, we want to send that into there. We don't need to do the +1 this time because we either want it to be off or on if the toggle is going to be 1, and we'll do a load mess 0 here, so by default training mode is off. Send that into there. Great, and then the output of this we want to send exactly the same as we did here with the correct output. We need to target every voice, so we're going to do target 0, send the bang into that, send that into the first inlet polytilde, put this over here a bit so it looks a little bit nicer, and that into there. Spot on. Right, we're nearly there. We want now for the ZL group object, just in case anything gets messed up with its grouping and it receives the wrong number of items, that can seriously knack up the patch. I've had problems with that when I was testing this myself. So what we're going to do is put a little message box which says ZL clear, and that's a general function for pretty much all of the ZL objects, which will clear anything it's currently got stored in it. So we want that there so that can reinitialize that when we want it to, and we want it to do that when the list of inputs is first being sent in. So whenever a new set of inputs is coming in, the very first one of those, we want that to trigger ZL clear. So if you remember here, we've got the index of which of the inputs it's going to be. So we'll do cell 1, so when it reads that one of those is 1, it will send a bang out of there into that ZL clear, which will then clear the group before it sends everything else into there. So that should then group them correctly. Okay, the final piece of the puzzle here is for registering and outputting the weights so that we can read those. So we want to do a B3 object, and the B object is just for using multiple bangs at once. It's essentially like you're using trigger and just putting B, 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 however many. You just put the argument, that's however many bangs you're sending out. So again, first we want to do a ZL clear to this other ZL group object, which is going to group all of the weights out exactly the same as if we were doing the inputs. So we'll do ZL clear and send that into there. So it refreshes it. And then another target 0, because we want to get all of the weights. Send that into polytilde. And then finally send a bang into this final inlet of polytilde, because if you remember, that is expecting a bang to register that, so that it sends out all the weights. So then we send the output of that ZL group into a list funnel object, which we will give the argument of 1, so that the first index is 1 instead of 0. So that'll be just more simple to read rather than reading 0 first. It'll read 1 first, so that's fine. I'm going to do outlet. Yeah, if you can't tell already, it's been a long week. I'm quite tired, but I wanted to get this up for you guys because I know it's good fun and a few of you have been waiting for it. So this second output will be all of the weights. Can't even spell. Weights list. There we go. And if I am correct, that should be our final neuron. So if we save this as neuron underscore mark1, close that down, make a new patcher, new object, neuron mark1 space, do argument of 3, lock it, go into it. Perfect. Yep, so load mess3 into voices. So that looks about right. Perfect. Now I could build the patch that will put our information into that, but that'll just be a little bit labour intensive. You don't need to see me doing that. So here's one I made earlier. Neuron abstraction testing. Now it's obviously lost where the neuron Mark 3, not Mark 1 object is, because I named it slightly differently because I'm an idiot. So if we rename this neuron without the underscore, then reload this patch, that's better. So yeah, that's proof, yeah, case in point of naming things properly. because otherwise Max just doesn't know what you're talking about. So here we go, and if I load up this preset of the different matrix control objects, we've got this first set of data like we had before. So initialize all of the weights with a bang into the first inlet, because if I unlock it, you can see here, you hover over, initialize weights, bang. And then this one, if we turn the toggle on, I didn't name that one, but if we turn the toggle on, that starts training mode. So then if we press this, there we go, so it's gone through the whole of training mode. And here if we do 0, 1, 1, the output should be 0. Yep. If we do this, 1, 0, 0, the output should be 1. Yep. And then here the output, as before, is 0.4, but the output here is very close to 0 again, so that's correct. So the way I did it slightly differently, I did a set of training data which had 6 rows instead of 4, and I did it so that we have one extra one with the second inlet being 1, obviously showing that the output is different to that. So that should now, if we reinitialize the weight, turn training mode on, and send this one out instead, obviously we've changed the Uzi argument for how many rows there are, send that out, we should now, if we try this, we get 0.01, which still isn't as good, but it's much closer to 0, so this is a much better result now. So that's great. And then just to prove that the Neuron does work with multiple inputs again, I created an entirely new list of information which is still following the same rules as this. The last column here is the correct output, but in this case the third input is the correct one and all the others are incorrect. So here if we initialize all the weights, turn training mode on, bang, takes a couple of seconds longer as you can see there, then turn training mode off. Here if we do 0, 0, 1, 0, 0, if remember the third one is the correct one, this should be 1. Yeah, here it should be 0. And then with the rest of these it should all be 0, but I've done a few just to test if there were any of the inputs that was a rogue that had not been done properly or whatever reason. So if we go through these, that's fine, that's also fine, that's again not completely ideal but still more or less fine, that's fine, and that one is not fine. Now that's a good example of where it's still not done it right despite how I've set it up. So here if we change a couple of these values, change that to that and maybe that to that, and then if we save that, reinitialize it, redo it, and then we'll test this again, we now get 0.35. So again, could be better, but we know more or less what it's saying. Okay, so that is Neuron abstracted, working, able to be built as an object. So that's lovely, so that works. So the next time we are going to go from this article that we had before, which is building a simple neural network, and we're going to change it into a multi-layered neural network, which will be designed to read the output of an XOR gate, which is a little bit more complex and will require us to actually build a neural network as opposed to an individual neuron. So I look forward to seeing you all next time. Thank you very much for watching. As usual, the patch will be available on my website. Please check the description. Thanks. See you next time.